Hello. So this is basically lecture 5.5. I'm going to go over some topics that we weren't able to cover in lecture 5. And those are going to be the function call dependency graph and the call stack. Alright, let's start. So function call dependency graph. These are some pretty big words. Let's try to split that into several parts. So the first, a function call. What is a function call? So hopefully by now you've seen lots of function calls. Whenever we define functions like f, cube, and square here, we can call those functions that we make. So give it some values for its parameters, and if you run a program while calling a function, you should get whatever output you expect. So that's what calling a function is. How about a dependency? So back in lecture 4, we went over how we can design our programs in layers. Dependencies are essentially how we relate those layers together. So here's sum of cubes until we say that it depends on sum until. So remember when we had our composition example, in order to express sum of cubes until, we just squared the call to sum until. So that's why sum cubes until depends on sum until. And the last word here is a graph. So you will be introduced to graphs when you get to CS 31 for the CS people. For the math people, take note that these graphs, these are not the drawings of functions that you might be familiar with. Instead, as you'll see later, graphs are going to be things or nodes that have arrows connecting them. Alright, so function called dependency graphs. For my CS lectures, you might have seen me using stuff like this, so show calls. Essentially what this does is it shows what function calls I'm making whenever I am calling a function. So if I put that in all three functions here, show calls, and now I run this, I see that these function calls are made when I run this left program over here. So an FCDG is essentially kind of like this, but the main difference is that for what I'm showing here, I'm showing the function calls in a list format. So here we have the first function call, the second one, the third one, and so on. For function call dependency graphs, they're going to look something like what you'll see in the next slide. So programs, whenever you run them, you can visualize them as either a tree or a graph. When we say tree, we don't mean puno, we mean a special kind of graph. It's a graph without cycles. Let's go to the slide. So this, what you see on the right here, is what a function called dependency graph looks like. So for the left program, its FCDG looks like this. Notice how the function calls you see here, they're the same things as what I've shown here. This is just the list version of all of the function calls and the arrows between them. So each arrow here is a dependency. So we say that f of 543 depends on calling the function square at 5. Similarly, it also depends on calling square with input 4 and calling cube with input 3. So this f543 has 3 direct dependencies, these 3 function calls. Yung cube of 3, since it makes an inner function call, here is where cube is defined, and notice how it calls the square function. So we say that if we call cube with an input of 3, that depends on the function square. So cube depends on square. So what does this look like for recursive functions. If we try to visualize the recursive function I have over here, if I try to run this now, we see that we get 43210. In fact, it's pretty similar to what you see here. It's literally a list, but there are arrows between the function calls. So notice how this graph looks a lot more linear compared to this graph. Here you go from one to another, then to another function call, and so on. Here your function calls sort of branch out, so a single function call here, yung f, can have multiple dependencies. But here, it only has a single dependency. So the number of dependencies will largely vary depending on how you define your function and what other function calls you put inside its definition. So yeah, that's what an FCDG is. Alright, let's now go on to the call stack. So as we've gone over, any complex computation that we want to achieve, that's basically a composition of function calls. So in this case, to implement f, we just composed yung square and cube functions. So here, so whenever we make function calls, Python treats them, or Python runs them using a stack. So you can imagine a stack of plates. You can either remove a plate from the top of the stack or put a plate on top of the stack. So as you can imagine, a stack grows upwards, at least this stack of plates, it grows upwards, and as you remove elements from it, it goes downwards. So that's what we call a last in, first out structure. So last in, first out. So if you imagine here, the last plate that you put in, if you want to remove a plate, that last plate that you put in is also going to be the first plate that you put out. That's why it's last in, first out. So what's with these stacks? Alright, so this is the program on the left we had here. So this, let's try to see how Python runs this program. So here we have the program as well as a stack. You can imagine each rectangle here as a plate that contains the function call. So we start by calling the print function on f543. Afterwards, since we're calling f of 543 here, we put in another plate called f that contains whatever its definition is, as well as the values that we pass in as parameters. So x is 5, y is 4, z is 3. So the first inner function call in f is square of x. X here is 5. So we put in another plate, the square for square, with n is equal to 5. So we set this n to 5. Once we have that, we can simplify this part of the function call. So square of 5 is 25. So this is replaced by square of x is replaced by 25. Next, the next function call, as you can imagine, is going to be square, but this time we pass in the value of y. Y is 4, and so we give it another plate called square, whose input is 4. Once we've returned from square, we remove the plate and we're back to the function f. So here, square of y, or square of 4, was replaced with 16. So far, you can think of the call stack as just adding or removing plates where each plate corresponds to a function call. So if we continue this, the next function call that we make is cube. So the next plate we put on here, we simplify the 25 plus 16 first, then put on the cube plate, whose input is n is equal to 3. So here, as you can imagine, 3 cube. Here, the way we implement cube of n is by making an additional call to the square function. So on top of this cube plate, we will have a square plate. So we have a rectangle or plate for this call to square with n is equal to 3. So this call to square is represented by this topmost plate we have here. So inside square, as usual, we simplify that. So square of 3 becomes 9. 3 times 9 becomes 27. And since the cube has now returned at this point, the plate corresponding to it has also been removed. So we remove the plate for cube, and we're left with 41 minus 27. That's equal to 14. So we print out 14, and that's essentially how our program runs. So what happened throughout this process? So we had two main operations. So first, there is a world of variables. We'll go over that later. And this world of variables is in the form of the stack. So this entire stack of plates here, imagine that whatever parameters we have or arguments we have for our functions, you can think of these as variables in their own right. And essentially, what we're keeping track of here is what those variables are equal to. What's more important? Each element of the stack, each plate that we had, that represents a function call and contains its own variables. So our two operations are pushing something onto our stack, so putting a plate corresponding to a function call, as well as returning from a function call. So getting something from the top of the stack, popping it off. So as we had over here, whenever we had new functions, we would push them onto the stack. Once we're done with them, we pop them off from the stack. So that's pushing and popping. So when you're designing your programs like this, you don't necessarily need to know how the call stack is operating at each single point in time, since, as you can probably imagine, that's quite a lot of work to do. So aside from writing the actual solution, if you had to keep track of what the stack looked like at each point, that might get pretty confusing. So our advice is to try not to think of it too much, because ultimately, in order to execute functions or function calls, that's ultimately the computer's job, not yours. So yeah, as much as possible, you don't really need to concern yourself with what's happening with the call stack. So now that we've shown the call stack for a non-recursive function, how about for a recursive function? So here we have the factorial function. What happens if we try to run this? What happens to the call stack? So this is how we defined it, and this is the program we have over here. Alright, so does a function being recursive change anything about how the call stack works? In fact, it doesn't. So your computer doesn't really care about whether this function, whatever function it's running, is recursive or not. All that it cares about is the fact that there's a call stack and it has to push and pop things off of that call stack. So let's start here. So we start again with printing the factorial of 4. So this is the bottommost plate in our current stack. First, we go over here. So we call the factorial function, 4 is not equal to 0, so it looks inside this branch. So it has 4 times factorial of 4 minus 1. N is equal to 4, so this is 4 times factorial of 3. Factorial of 3 is yet another function call. So we put on another plate with n is equal to 3. As you can imagine, we do pretty much the same thing, simplify that, and make a call to factorial of 2. Do the same thing again for factorial of 1 and for factorial of 0. Once we reach 0, we look at this branch instead of this branch, since n is equal to 0. So if n is equal to 0, we end up returning the value 1. So factorial of 0 is equal to 1. And so this evaluates to 1. So once that is done, we can simplify the rest of the function calls here. 1 times 1, 2 times 1, 3 times 2, then 4 times 3 times 2, or 4 times 6. So after all of that, we end up with 24 over here. So we end up printing the value 24. So that is how the call stack works for recursive functions. As you can see, this is also why it's important to make sure that your recursive functions have a base case. So if they don't have a base case, you can imagine this stack would just grow on forever. So -1, -2, and so on. If the stack grows too much, you end up overflowing the stack. That's why we have terms like stack overflow, since if you put too many plates onto the stack, Python basically gets mad at you. So that's also the reason why Python has a recursion limit. If you exceed that recursion limit, the amount of plates you can put at once onto your call stack, you would get a recursion error. So yeah, that is the call stack. Alright, so finally, which of these two visualizations should you use? So again, we recommend just thinking of the function called dependency graph instead. So here, instead of worrying about what plates you put on or pop off from the call stack, we recommend just considering the different function calls and the dependencies between them. So yeah, it's slightly better to think of the FCDG. So actually that's it for this mini lecture. If you are curious about the call stack, you can also use the other decorator that I added here. So show call stack. If you use that instead, so if I have that now and I try to run recursive.py, each start here corresponds to putting on a plate onto the call stack, while each end over here corresponds to removing a plate from the call stack. So yeah, that's also something you can play with. But yeah, that's pretty much all I wanted to go over for lecture 5.5. If you're getting confused with how your function calls are being executed, hopefully this is more helpful as a visualization. So yeah, that's it for this mini video lecture. Thank you for listening.